You saw that I uploaded Lab 3 this morning. Jordan said that he was going to get them all graded this week. That's as far as they are completely graded at this point. If you have, one student came up and talked about the grade and had a problem with the grade. If you have a problem with the grade, please definitely first contact Jordan Bissell, Jordan. Just send him an email and send a carbon copy to me. And if you don't think that you reached a fair outcome with Jordan, then follow up again with me to let me know. Okay. I don't want to just undermine my TAs. I want them to be trusted and so on. So that's why I asked you to first talk to him. Speaking of which, anyone who is interested in being a TA for this class next semester, please come talk to me because I am always looking for TAs. What about the test? The test, I have 2 more problems left to grade. I am working on getting that done. We'll see how progress is made. It will be done definitely before I go to, before sundown Friday, not before I go to bed Friday, because clearly I'm not grading after sundown. Michaela.
Will you make one of those Excel sheets like you did last semester to calculate our grades?
I might, although I looked at my son's grade and it's working properly, at least for his class. Maybe it's the way it's put together, but I will have something for you to be able to determine, yes. That is, with his, it actually tells him, if you get this grade in the final, you'll have this overall grade. That's the way it's supposed to work. It might be because I have a calculation, that's why it doesn't work for this class. Okay. I'm looking at the wrong column. There it is. We're going to talk about radiometric dating. We're going to do it. It's going to be today. Anybody recognize this picture? Have I talked about it at all in this class? Okay, I did. Okay, good. First, a clicker question. You can't answer yet because I got sidetracked. We'll all blame Amanda for this. I was starting this up when you came, and then I forgot. Okay, why must neutrons be, quote, thermal to produce a nuclear fission chain reaction is the question. Make sure you know what the word thermal means before you answer. And I am ever so close. It is now open for answers, and Edward was, boom, in there the second it was open. He was mashing the button, waiting for it to be open. Okay, people who have not answered yet are James, Brittany, just Brittany. I only have, there we go. Okay, we had a fairly even split. Amanda Mikata. I used to pronounce the president's name Jimmy Cotta. That's Amanda, give us some insight.
I was for B, and I was thinking if the neutrons are too fast, it just wasn't able to absorb at all, like it couldn't interact with them. So we needed to be a certain speed.
And she is exactly right. Now, we only talked about uranium. The graph had both on it. but they can only absorb effectively if you have a slow moving. Thermal means slow in this context. A slow moving neutron. So this one here was wrong. The one that the roughly other half of the class answer was wrong because fast is what they cannot absorb. The way I think about this in my head is not exactly correct. I just think about it as the slow one is interacting with the nucleus for a longer period of time. That's not exactly the reason, but it works for me. One that two people answered, plutonium and uranium can only absorb electrically neutral neutrons. Can somebody quickly point out the flaw in that answer? That's right. It has that neut. That means it's neutral. All neutrons are neutral. So that one was not a distinguishing factor. The last one, no one answered. What was genetically wrong with the last one? You may or may not know this, like, the last one you should have all known. This one you may not know. It's genetically wrong with the statement for D. Yeah, neutrons are just like electrons in that they have a spin of 1/2. So it's just not possible to have a zero spin neutron. Okay, radioactive decay. We did a lab with radioactive decay. In that lab, you measured the decay, the activity, the number of decays per second for 90 stinking minutes, or 80 minutes, somewhere between 80 and 90 minutes. And what did you observe as you did your experiment? Just summarize what you observed. Go ahead.
Some of the bands, at first it would drop quickly, but then it started dropping slowly.
Okay, so initially, the activity, the number of decays per second that you measured, was dropping rapidly. But over time, it started dropping more slowly, more slowly. The reason is because you have each radioactive atom has a certain likelihood, a certain probability of decaying in that minute. And so if you have lots of radioactive atoms, you have lots of them with this certain probability. So statistically, the statistics are reasonably good with the number of nuclei we have. You should have a large number of decays because you have a large number of atoms. But when those atoms decay, the number of remaining atoms are less. And so each minute, there's less atoms that can decay. Hence, the same percentage of them will decay, but it's less total. And so that gives us this nice decay curve. And we talk about the time for 1/2 to decay. Now that's a probability statement, is the half-life. So if you start with 1 million radioactive nuclei in one half-life, 1/2 of them should have decayed if statistics are going to play out exactly right. So that's where you have the 500,000 after one half-life. After a second half-life, half of those that remained after the first half-life will have decayed. So half of 500,000, 250 remain. Go a third half-life, half of those 250,000 decay, 125,000 remain, and so on. So that shows you the sequence that occurs, helping you to understand better the idea I said about the probability. Well, we can use this then as a way to measure times. If we know how many we started with and we know how many we have now, we can calculate how long it's been. So that's the basis for radiometric decay. Now our second and final clicker question, which is not open because of the fun, enjoy. Now it's open. Approximately how many half-lives result in less than 0.1% of the original nuclei remaining? Remember, each half-life you have 1/2 remaining. So after n half-lives, you have 1/2 raised to the n remaining. those in computer science have a benefit here because they know what 2 raised to the 1, 2 raised to the 2, 2 raised to the 3, etc. is. Just one. All right, everyone's answered. Okay, one person said 1. That person missed our discussion. What does half-life mean? What is the definition of those words? The time it takes for half of the substance to decay. So after 1 half-life, you would have 50%. Because half of it's decayed, half remains. So that one, definitely not close. Now, the rest of them, you could have done trial and error. You could have done it strictly mathematically. If you want to do it strictly mathematically, you would say, well, 0.1%, which is 0.001, is equal to 1/2 raised to the n. So if I take the natural log of both sides, and then use the rules for natural logs, I could have done this calculation and given me an exact number, but of course, that number is going to be fractional. What is that exact number? It's what?
9.97.
Okay. It's actually positive because there's a minus sign here, and the natural log of 0.001 has a minus sign. So it's plus 9.97. So what would the correct answer be then? 10. And how would I have calculated without doing it strictly speaking? I would have said, well, 2 raised to the, let's go with, if you're in computer science, the easy. Compute 2 raised to the 8 is 256, right? You have 256 bits in a byte. And then if I go another factor of 2, 2 times 256 is 512. So that's 9. Another factor of 2 would be 1024. So 2 raised to the 10th power is 1024. 1 over 1024 is very close to 0.001. Or, of course, I had it on this slide. But that's not something you had to look at. Now, how do we do carbon-14 dating? How many people have heard discussions of carbon-14 dating? And of course, everybody in origins class, like Noah and Christian, should have raised their hand, because we've discussed it. Carbon-14 dating to young Earth creationists is very important. To people who believe that the Earth is 4.5 billion years old or 4.6 billion years old, and how you want to round it. I usually round it to 5 billion. Carbon-14 dating is insignificant. So in our lecture Monday, for the three of you, what dating did he talk about? It was still radiometric. Okay, in zircons, measuring the uranium lead dating, and he used uranium-238 as well as uranium-235, pointing out that uranium-235 is less than 0.5% of the naturally occurring, actually I think it's around 0.5% naturally occurring uranium. When he said that, Noah looked knowingly at me, made me feel proud. She picked that up in class. So 2 uranium lead decay sequences, as well as a thorium decay sequence. So those are used by old Earth scientists because they have longer half-lives. Carbon-14 has a half-life of 5,730 years. So 5,730 years, you're going to have half the carbon-14 you have now. In 10 half-lives, you'll have about 0.1% of that. So around let's say 60,000 years, you'll have 0.1% of the carbon-14 that's in the atmosphere when it starts. And there's so little carbon in the atmosphere right now that there is essentially no chance of having any carbon-14 remaining after about 60,000 years, after around 10 half-lives. So carbon-14 dating can only date out to somewhere in the ballpark of 50 to 75,000 years. Anything older than that, carbon-14 dating is useless for. Your uncertainty is going to be bigger than your measurement. Question?
How do you know exactly how much that was in the beginning if we weren't there?
That is a question I'm going to answer, because that's a really vital question. So how does carbon-14 dating work? First, you have organisms. It only works with living organisms that die. Living organisms are eating food, and that food is in the form of vegetables and fruits. Now you might say, I caught you. Think of the lion. The lion is a hunter, and it eats wildebeest, right? And other things that it finds in the range. It doesn't eat plants. But what did the wildebeest eat? Eventually, everything is getting its nutrition from plants. If you're eating meat, that meat, yes, is processed, but it got its material from plants originally. So anything that's eating food is bringing in plants. Those plants undergo photosynthesis where they take air into them and they produce energy. Well, in the process, they then take in carbon atoms that are in the atmosphere. And the carbon in the atmosphere contains both carbon-12 and carbon-14. Why does it have carbon-14 in it? Carbon-14 is radioactive, and after 50,000 years, it should be none. But the fact is, you have neutrons that hit a nitrogen that produces a very unstable. So that star means it's unstable. That pretty much immediately breaks into a carbon-14 and a proton. Now, I think that's the complete reaction there. And so carbon-14 is made in the atmosphere because neutrons flying at us from the sun are absorbed by nitrogen, which is 79% of the atmosphere, creating carbon-14. So carbon-14 is in the atmosphere, it's in the air that we breathe because of the sunlight, the sun's radiation. So it's constantly being made. Then you measure, when something dies, it stops eating. It's kind of convenient. And so the amount of carbon-14 in that object is locked in. It's not taking in any more carbon-14. And what the scientists measure is the ratio of carbon-14 to carbon-12 in their sample. And they compare that ratio to the ratio in the atmosphere. Now, this goes to Etika's question that I'm going to answer. Just want to make sure it's still clear. That's a question on the table. You have to know what the ratio was when you started, so you can compare the ratio now with the ratio you started with and determine how long it's been since it stopped eating. So when you're doing carbon-14 dating, you're effectively measuring how long has it been since this organism stopped eating or stopped undergoing photosynthesis. And so this is just showing, what the ratios are as a function of time. So the assumptions. The initial assumption that is immediately thrown out and replaced with a better one is that carbon-14 to carbon-12 ratio has been constant for all time. That's an initial assumption. When we start explaining carbon-14, we start with that saying the ratio is known because we have, the sun causing it. But the sun's activity can change over time. So at some points in time, the sun will be spitting out more neutrons at us, making more carbon-14 in the atmosphere. Other points in time, less. Sometimes we will have eruptions of volcanoes on Earth that will change the chemical composition of the air. So we know very specifically that this ratio is not constant. In fact, I'm going to show you a couple graphs on the next slide. So instead of saying it's constant, we say it's well calibrated. And once again, I'll show you a slide that deals with that. So I'll get to that in the next slide. Another thing that's assumed is that the half-life of carbon-14 is constant. Once again, Jerry mentioned that in his lecture on origins on Monday. What if the half-life has changed over time? Well, that would screw up the whole carbon-14 and, in fact, all radiometric dating calculations. We have no reason to suspect, realistically, that it has changed. Some people have made observations about the measured values for the speed of light. What difference does that make? Well, the electric force is dependent on the photon is related to the speed of light here. So it actually would affect the half-life as well. And the speed of light measurements over time have shown generally a downward curve. And so people say, aha, the speed of light used to be faster and it's slowing down. But what they're missing is the uncertainty in the measurements is always big enough that the true value pretty much fits into every one of those measurements. So you don't have a true trend. You just have people's measurements have really big uncertainties, and as they refine things, the uncertainties got smaller, they narrowed in on the low end of what their measurements were. Another assumption is that organisms maintain the same carbon-14, carbon-12 ratio as in the atmosphere during their life. That's one that we can test today. We can test animals and plants now and see if the ratio of carbon-14, carbon-12 in them now is the same as in the sky. And if it is, then that's a good thing to say that that's probably a correct assumption, which is verified out by experiment. And, of course, the organisms don't exchange carbon after they die, which I hope they don't. Here's some examples of carbon-14. Looking at the amount of carbon-14 in things that can be dated, we find that the amount of carbon-14 in the atmosphere varies reasonably dramatically. So you have these different minima and maxima. What are those talking about? They're talking about solar activity. When the sun is more active, you have a maximum like the medieval max or the modern max, which is where we are now. The sun is more active right now than on average, which means that we have more warming right now than we have on average, higher temperatures. We have minima here as well. The Maunder minimum is a very famous cold spell on Earth. It was cold because the sun wasn't producing as much radiation. And you can see that the carbon-14 ratios varied with that as well. This one here, of course, I love this because my birth is right. Okay, not quite. There's my birth. So just a few years before my birth, the amount of carbon-14 in the atmosphere spiked. And then it's been coming down since then. It only goes till 1970. And you're like, why would the carbon-14 level have spiked there? That's a pretty significant jump, right? Because you're going from around 400 to above 800, more than doubling the ratio. Well, there was a volcanic eruption that corresponds with this. It's believed that because of the volcanic eruption, the ratio changed considerably. So how do we account for this, right? That goes to Erika's question. We can't just assume that the carbon-14 to carbon-12 ratio was constant in all time. So what scientists do is they look for artifacts and they measure what the ratio is today. And if they have an artifact that has a known age, something that can either be documented by historical records or they can be documented by things like looking at growth rings in a tree. On average, there's one wet season and one dry season a year. And so you have one band produced in a tree every year. And so by looking at tree rings, you can get some idea of ages. And you can see here some of the specific things that are used for the calibration curve. And this is showing a smooth theoretical curve. The actual calibration curve is not the smooth curve. It's the most accurate connect the dot type of curve using all of their data points they can for calibration. So they calculate what the ratio of carbon-14 to carbon-12 was in the past based on things that they can use for calibration. And here's a very practical example. I know I used this when I was lecturing on this in Origins class. Ötzi the Iceman. Ötzi, and of course we talked about a lot more because it was a whole lecture in Origins class, but it was a person who had been encapsulated in ice and frozen for a very long time and was found by hikers just hiking along and, hey, look, there is the remnants of a person. And it was in the Ötzi Mountains or something, so that's why it's named Ötzi. And so it's been radiometrically dated. And what they found was a specific carbon-14 to carbon-12 ratio. And if you used uncalibrated data, it would have given you that Ötzi was about 2,500 years BC. That's about the time of the flood, actually, by traditional biblical reckoning. 2,500 years before Christ, or roughly 4,500 years ago. But that is not the age that they give to Ötzi, because they go through using the calibration curve. And going through the calibration curve, this calibration curve you see is very wiggly because it's saying this ratio, and this shows radiocarbon age, but it's actually based on the ratio. This ratio of carbon-14 to carbon-12 should occur now if the sample came from the range that's shown with the squiggly graph. And so if you zoom in, which is what is done right here, you have that squiggly line on the graph crosses over here, comes in here, and comes in here to, I believe that's plus or minus 1 standard deviation lines. And so the conclusion is Now, you might suspect this here is the only one that goes through the center. And so you might suspect this must be the true age right here. This is 2 standard deviations. This is 1 standard deviation. So somewhere between 3,300 and, well, let's say 3,350 BC is about the time of Ötzi. But there is also a reasonable chance, much smaller probability, of being younger in this time frame or this time frame. And so for the actual measurement, it's not so simple. They don't just say, Ötzi died somewhere around 2,500 BC. They break it down and say, Ötzi died, and we have a couple ranges here. With 68% confidence, we can say between that time period. And you can break it down even further into smaller time periods, as you see here. So it's much more complicated in what they do with it. It's not some simplistic, they didn't think all the physics through option. It's actually well thought through. Now let's look at this specific example, the Shroud of Turin, or Torino. It shows an imprint of a person. And the story is that this is the face of Christ you're looking at. That's what Christ looked like. Now, what is there evidence to say that this was actually the burial shroud of Christ? I am not certain. But what I am certain is that it was found in the 14th century. And in 1988, they carbon dated it to 728 years old in 1988. Now, 728 years before 1988 would put its origin about 1260 AD. 1260 years, Anno Domini. Anno Domini is the year of our God. So 1260 years after Jesus was born. It's unlikely that the death shroud used by Jesus would be dated to something that was over 1,000 years after his death. After all, how old was Jesus at his death? 33. Started his ministry at 30 and ministered for 3 years, if I remember right. So that would make it seem very unlikely that this is actually the true shroud of Christ. And in fact, if you notice, there is a nice correlation between this and when it was found. It was found in the 14th century, 1260 AD, is 40 years before the 14th century began. And so one could say, yeah, that's pretty much, they found it when it was not very old. It was maybe 50 to 100 years old when they found it. Now, if you're a true believer in the Shroud of Turin, you don't give up. And so true believers that the Shroud of Turin is the robe, the shroud that Jesus was wrapped in, say, but you know what? They didn't want to damage the shroud. And you have to damage it to do the radiometric dating. You have to take a sample and you have to decompose it. You have to do stuff to it. And so they took a little piece of sample from a damaged portion of the shroud already. And that damaged portion had material that looked different than the rest, and the theory is that it had been mended. And so maybe they got a date for when the shroud was mended rather than when it actually was made. And of course, the only thing to do then would be to find another sample that they can all agree, yeah, this is original stuff, and test that. And as far as I know, that hasn't been done. But the true believers say, look, you just tested the wrong place. You got a bogus answer because you tested the wrong place. But that's an example of radiometric dating that I find very interesting. I am going to move on to something important. We have just a couple more topics here, and then it's review. How much review today? Very little, I'm sure. Radioactive decay. Is it important to you and me? It's important in some regards. The Earth of course, we have to have energy resources for things we do. And what supplies most of our energy? The sun. The sun is over 99% of all of the energy available to the Earth. It is our big energy resource. The sun is what drives our weather systems, so wind power is derived from the sun. The sun is what allows plants to grow. So when you're using ethanol fuel in your car, that is derived energy from the sun. Even fossil fuels is made from formerly living things. That's energy derived from the sun. So virtually every source of energy you can think of is derived from the sun, except for a small fraction that comes from radioactive decay. Radioactive decay is responsible for things like the core of the Earth is still cooling. When the Earth formed, according to scientific theory, you have an infall of material. And as it falls in, it goes faster and faster because of gravity. Faster means higher temperature. Huge energies. The Earth, theoretically, was initially completely molten, a melted object. And so the most dense material, iron, sunk through. The least dense material, silicate and oxygen, floated up to the surface, giving us the crust that we're used to that's largely silicate rock. It's, 92% silicate rock, I think it is, something like that. And the core being largely iron. And then the Earth has begun cooling. And so, of course, the crust cools, and you get the rocky lithosphere. And then cooling continues. It's actually a really cool acoustic effect right here. The cooling continues, and you have now a frozen mantle, but you still have a molten core. And part of what keeps that core molten is that there's energy being released by radioactive decays in the core. Why radioactive decays in the core? Well, uranium, being a primary radioactive rock, is very dense, much more dense than lead, which is far more dense than iron. So the vast majority of uranium in the Earth should be in the core. And so the radioactive decay, each decay is having the nucleus go from a higher potential energy state to a lower potential energy state, giving off the energy difference, releasing energy, making it hot. So we have radioactive decay in the core that's keeping things warm, making it so it doesn't cool as quickly. And here it's showing you got lots of radioactive particles flying around in there. One of the things that we worry about, especially living out here in Nebraska, is radon gas. How many people have worried about radon gas? Wow, not many. Well, radon gas is a radioactive gas that is produced in the decay sequence of uranium. In the decay sequence, you go uranium, just talking about the alpha decays, uranium, thorium, radium, radon, polonium, lead. Well, radon of all of those is the only gas. But that decay means that naturally occurring rock is going to be producing this radioactive gas, radon. And so that's how you get the radon in your basement. Radon is a pretty dense gas, so it's a heavy gas. It sinks in air. So you worry about a lot more in your basement than you do up high because it's not going to float up in the air. And it's radioactive if it decays into polonium, and that polonium then is in your lungs. When it decays, that polonium will cause damage to your lungs. And that's why you worry about it. Yeah?
So what do you do to get rid of this gas that's really heavy?
What do we do? It's actually really simple. I had this done in my house because the radon levels in my basement, they'd be considered safe, I think, is in Europe, but not in the United States. Right? So it's in an iffy zone of safe versus dangerous. But I figured, let's go with being safer. And so I had a radon remediation system put in my house. And what they do is they simply put a pump and suck air out of your sump pump, or your sump system. So you have drainage tiles in your basement out here, you do at least. And so you have a way for air to circulate under your house, and they make the pressure in those tiles lower than air pressure. So if I have air pressure in the basement and lower pressure underneath, what's going to happen to air? It's going to be pulled through the floor if you have a crack instead of going through the floor into the house. And so they keep the radon from entering the house by having a lower pressure underneath than you have in the house. So it's a pretty simple solution. And the radon itself doesn't last very long. So a couple days after the system's in, you should be fine. Yeah?
Why is this only a problem in Nebraska?
Well, it's not only in Nebraska. It's just not much of a problem in California. It depends on how much uranium-containing rock you have in your soil. And so it depends on the uranium-containing rock. And you can look at maps that show you places there you have more and you have more concern, less and less concern. Also in California, for whatever reason, basements aren't popular there. And it's much more of a problem in a basement than elsewhere because if you don't have a basement, you open the front door, it's going to flow out actually. And so it doesn't build up as easily as it would if you had a basement. Okay, some more interesting things. Tunneling. Anybody heard of tunneling? Go ahead, Corso, you can raise your hand. We talked about it on one of our Tuesday classes. No, not yesterday. We didn't have class yesterday. Corso missed a class we didn't have. Okay, well, tunneling is a very interesting phenomenon. And we can explain tunneling first by what the phenomenon is. Imagine that there is a wall that is between Angelina and me. And that wall is so high I can't get over it. So wide I can't get around it. How can I get through to Angelina if I can't go over the wall and I can't go around it? No, there's no door. I can't go in through the door. For people who actually recognize the song I was quoting the lines from. The answer that we come up with for scientific naming purposes is to say, well, if you were in prison and you couldn't get up over the wall and you couldn't go around the wall, then you would have to resort to tunneling underneath it, digging a tunnel that goes under that wall. That's what the name tunneling comes from. Finding a way past the barrier you're not able to get through. And so in quantum physics, we have systems where you have a certain potential energy. And this picture here is to be realistic. I'm going to show a picture that's not realistic. One like we did, well, we didn't do the second part, but we did a particle in a box in the 252 class. And so you have this potential energy well. So this graph has potential energy in the vertical axis, 0 at the bottom and some high value. And if your total energy is here, you don't have enough energy to get out of the box. You can think of the elevation just like you would energy because gravitational potential energy is mgh. So height, elevation, corresponds to gravitational potential energy. So you don't have enough energy to go to the height to get over the box. But quantum physics says that for a particle that's in this box, it's going to have a wave function. Remember we're talking about the wave function? Okay, a few people nod their head yes. For those who didn't, well, steady up on it for the final exam. But you have a wave function that tells you about the probability of the particle existing at any location. And the wave function in the box is going to look something like that for the first energy state. Outside of the box, it goes like this and goes towards 0. So here it's going to go like that. But the thing is, there's a second box here, and if it can get to here, notice the wave function isn't 0. There's a certain probability of it getting to the second box. It's not 0. And then once it's there, it's going to have another, thing like that. And so tunneling is the phenomenon that it's not allowed in here, but its wave function says there's a probability, if it's in the box, there's a certain probability of it being outside the box. And the thinner you make that wall, the better the probability that it's going to jump across the forbidden barrier. And so tunneling is, classically we talk about electron tunneling, is the electron moving from an allowed region to another allowed region, passing by a region where it doesn't have enough energy to exist. That's kind of like saying I'm going from California to Alaska, but I am not allowed to be in Canada, and I'm not allowed to take any ships or aircraft. So I'm not allowed to be in the space between California and Alaska, but somehow I make the trip. So in an atom, you have energy levels for things in the nucleus and energy levels for them outside the nucleus. They don't have enough energy to get out, and yet there's a certain probability that they will. And that's one way of modeling radioactive decay. It goes from a higher energy state in the nucleus to a lower energy state outside the nucleus, passing through a barrier that doesn't have enough energy to get out of. There's a much more practical, and so this is showing the alpha decay as a diagram. You're in the nucleus, you have an energy state that's here, doesn't have enough energy to get out. If it gets out of the nucleus, it goes away because of the positive charge that's repelling. It doesn't have enough energy to get out because of the attractive, strong nuclear forces, but it doesn't. We use this, going to just go past this. This is showing the wave function idea in things like scanning tunneling microscopes. A scanning tunneling microscope is made by taking a tip. So this is showing the tip here. And you make that tip atomically sharp. What does it mean to make the tip atomically sharp? No answers? Okay, if I didn't use the term atomically, what would sharp mean? Pointed. So this would be sharp normally. Atomically sharp means on an atomic level it's sharp. So on an atomic level, you're looking at, you have atoms like this. And atomically sharp, it's essentially coming down to a single atom there at the tip. It's not a bunch of atoms like this at the tip, which is what most sharp things actually are. So you make it atomically sharp by special techniques. And then you bring that tip really close to a surface and you apply a voltage difference. Not a big enough voltage for an electron to be able to arc from the tip to the sample, but a big enough voltage difference that there is a certain probability that it will tunnel through. Arcing would be it has enough energy to make it across. And then they bring it down and they measure the tunneling current. They measure how much electrons per second is actually crossing the forbidden barrier. And that tells them how close they are to the surface. And so with the STM, you're actually using this tunneling phenomenon to make measurements to the surface. Now, there's different modes they can make this. They can do a constant height and measure how the current changes, or they can use a constant current and go up and down to try to model the surface. Using this technique, they can make atomic-sized images of a surface. That is, you can see individual atoms. So one of the first things that IBM did back in the 1990s with this was they actually found a way to move atoms and then took a scanning tunneling micrograph of it where they had spelled out IBM in atoms on a surface. Which is really cool, being able to manipulate atoms and to measure that. So this shows a biological picture. Well, biology isn't the realm where you really want to use the STM. You can use like a scanning electron microscope to see plane resolution for biology usually, but this is used for really small detail. And it would be review from here, but it's 11:49, so we'll stop and we will review on Friday.